Hello, everybody. Welcome back to my channel. Have you ever wondered about how AI can help to design AI and driving the event of singularity? Well, ladies and gentlemen, here we have a new paper that talks about how to do that. So, um, yeah. So what this paper introduces, right, is a way to use large language models to design a neural network called graph neural networks. And this can help us to automate the workflow of uh, designing graph neural networks. So, in this video, we're going to talk about a paper called Computational-friendly graph neural network design by accumulating knowledge on large language models. And now, if we take a look at the instructions, what it says is exactly that. So, they aim to design proper architectures involving trial and error, right? And usually this takes a lot of human effort. So what they tried to do in this area is to trying to automate the design of graph neural networks. And what is graph neural networks? Graph neural networks are essentially neural networks that takes in graph structure inputs and produce an output, right? So, but obviously the current approaches are it requires a lot of computational resources in trying to testing out different candidate architectures, right? So that's going to be pretty expensive, and it also requires a prolonged process for the algorithms to accumulate knowledge about the relationships between the graphs, the neural networks, and the performance, right? So this is essentially a data set curation problem, right? It is expensive to get those kind of data, right? So so in order to do that, they have proposed a computational-friendly approach by using LLMs to design GNNs. And they claim that it can help to shorten the computational overhead. So what they really did is first by establishing a knowledge retrieval pipeline that comprehends the intercorrelations between the graphs, the neural network, and the performance. And, and then it converts the past model design experiences into structured knowledge for LLM reference. And it allows it to suggest initial model proposals. And after that, they use a knowledge-driven search strategy that emulates the exploration and exploitation process of human experts. So it's kind of like reinforcement learning in a sense. And this helps to make the refinement of the initial proposals quicker within the scope of the project. And they claim that their approach delivers a promising top 5.8% initial model proposals for unseen datasets within seconds and without any prior training, right? And and we're gonna have a look into this quickly. So if we go right into the conclusion, right? Oh, and by the way, we're not going to be covering the entire paper, but we will be covering just the gist of it. So, okay, right. So in this paper, they design DesiGNN, right, for designing graph neural networks using LLMs. So, okay, so the first integrate topological graph understanding and then specialized knowledge retrieval, right? It then produces initial GNN models that can be refined efficiently to align with the data set that you provide, right? And then Okay, and it is able to deliver top-tier GNN designs within seconds. Also, it has outstanding search performance in a few iterations. And they mentioned that while it's effective in graph domain, their approach is only limited to graph data and model, right? So a potential future research would be to develop more mappings between more data sets and more configuration space, and also applying it to other tasks such as predicting the link between different nodes. And this is something they could apply to image and tabular data as well, but that's for future research. And now we have an idea about the entire paper. Let's go through some things quickly. So, all right, let's see. Right, we're not gonna go through the introduction. Instead, we're gonna go directly into the methods, right? So, okay, let's start. All right, so the methods. The design of GNNs by both human experts and automated algorithms faces significant challenges, including substantial computational resources and lack of proficiency. So, okay, to address this, they designed DesiGNN, which we talked about earlier. So, DesiGNN is composed of three major different components, each designed to capture and leverage the relationships between graphs, GNN, and performance. So, okay, so step one. Graph Understanding module aims to analyze the graphs and identify the graph topology. And this is important to enable the LLMs to assess the similarity between benchmark and unseen graph datasets. Right. All right. So with respect to model preference, then they use knowledge retrieval module uh, that builds specialized model configuration knowledge from mass neural architectural search bench the graph so that the LLMs can utilize these insights gained from understanding graphs and retrieve relevant models as knowledge for unseen graphs. Right? And the last third component, model suggestion and refinement module, it uses the retrieve knowledge to suggest and to refine the GNNs that the framework proposed, right? So, okay, and that's it, right? So there's really three components in here. So let's see, okay, right. Let's go through the, okay, let's try to understand the figure by ourselves here. So we start off with an input graph. Sorry. Okay, we start off with an input graph that you're interested in. And then there is this graph understanding module here. And what you can see right here is that they extract a set of features, right? Such as the average clustering coefficient, the label homophily, and the average betweenness centrality, right? And and all these features get extracted directly from the graph. And then if we take a look at here, they have a data set, right, of neural architectural search. And I would assume that they have a set of known performance models, such as here, model 1 that we already know it achieves 80% accuracy, right? And model 2 achieves 79.6% accuracy. And then what we can do right here is that they can somehow get some information about this this neural architecture search data and try to identify the key features and incorporate it into this section right here as well, as far as I can tell, right? But for more accurate details, we have to go through each part of the methods, right? But right here, we're just trying to get some idea about the overall framework. So at the same time, it has this E rank and S rank. I'm not so sure what that means, but we shall see later on. And then I assume this entire graph understanding module then generates the unseen description. I think it's the unseen dataset description, and then somehow they can generate a set of similarity values for the unseen dataset. Okay, and then if we take a look at this part right here, the prompts. So they have to specify a unique prompt for the LLM, basically giving GPT-4 all of these information right here. So telling it about the data the data features and the task description, which is yes, please design a GNN for node classification tasks, and then you have to specify the search space, whether or not to incorporate some operations in the final model, such as a graph convolutional neural network or graph attention, right? And and then you give it to GPT-4 and you tell it that, okay, please generate a model, right? Suggest a model. And then if you suggest a model from that, and then you have to evaluate the performance of the suggested model, and then you have a feedback mechanism giving feedback about the performance of its own suggested model directly back into GPT-4. And right here, we have the last module here called the refinement module, which is actually the third module, I believe, which has which works by inputting the feedback, right, for each generation, inputting the feedback into the control exploration module right here, which they do some kind of a, well, this is kind of like evolutionary algorithm, right? To have this a crossover, which I think crossover between different designs. Not so sure about that either, right? And then they have this re-rank mechanism, which they didn't explain early on, but I'm pretty sure they do later on. And they do some kind of a ranking between data sets, right? Not so sure about that. And not only that, but they also have this model promotion mechanism. And I think model promotion mechanism is just a way to like rank the different model candidates and then giving the best one to GPT-4, which, that makes sense. And not only that, but then they have also like a reorder operation here, reorder knowledge pool that goes into here. And then it might even suggest the top end models for each different data sets, right? One for computer science, one for physics, and the other one for PubMed, right? So this is a rough overview of the figure. Obviously, I could have get something wrong here, right? But we shall go through that in more details right now. So, okay, right. Step 1, graph understanding module. To effectively accumulate tailored knowledge for specific data sets, you need to first understand the characteristics and structures of the graphs. All right. So, and how do they do it, right? And existing LLM approaches rely solely on user semantic descriptions while ignoring graph topology. Okay, so right, where did I start describing it then? Okay, as discussed previously in previous works, the semantic description may be biased, thus to achieve the goal about graph to GNN to performance, right? We start with 16, right? So that start with 16 graph features. For example, average shortest path and blah blah blah. So to have it in the appendix, if we go to the appendix, they actually show all 16 of them, namely initialized order based on their competences. Okay, right, okay. The average clustering coefficient, average betweenness, centrality, density of the graph, average degree centrality. So there's a whole bunch of features here from graph theory that they use. So now we understand that. Let's go back to the main text. All right, so they give it those descriptors, right, of the graph, and they and to understand. Okay, so it is used to generate a graph similarity from based on the similarity among graphs and the impact of graph similarity on the performance of the GNNs. Okay, right. All right, given two graphs, GI and GJ, right? For example, right, we have two different graphs, GI and GJ. Let SI and SJK denote the statistical value of feature FK on graphs GI and GI and GJ respectively. Then you have some kind of distance metric here that compute the differences between the features between the two different graphs. And it's stated that, for example, right, a negative distance can access the topological similarity. Well, obviously, the lower distance you have, the more similar the two graphs are. Then, to capture the difference between model performance, we let Pij denote the performance of transferring model configuration knowledge from one graph to another. Okay. In other words, Pij tries to assess similarity between graphs based on the effectiveness of knowledge transfer. So it is essentially what is the empirical performance when you transfer from one graph to another graph, right? So that's essentially that. And then define the statistical ranking called S rank and the empirical ranking E rank. Okay, so essentially they are just argument sort functions in these ranking functions. So okay, right. S rank is essentially the statistical similarity ranking of other graphs to graph GI based on feature FK, and E rank is the empirical similarity ranking of other graphs to graph GI. So to capture the impact of graph similarity on empirical effectiveness of the suggested GNNs, they use candle rank correlation coefficient between S rank and E rank. Yeah, so it is essentially from what I know, it's a nonlinear. Is it a nonlinear correlation? Let me see. Okay, right. So it's candles tau linear maybe is it linear? Yeah, I think it's linear. Yeah. So okay, that's good to know. Yeah. So okay. So the correlation between the statistical differences in FK between G1 and other graphs, right? So and the empirical differences in transfer knowledge between other graphs to GI. In other words, this correlation function here can be seen as the confidence of the graph feature to determine the empirical similarity between GI and other graph data within our knowledge. That is, if the larger the I value is, right, the more FK is a strong correlation indicator, right? It's a strong correlation indicator on GI that can determine whether or not other graphs is related to GI from the perspective of graph topology, right, and performance. All right, and in figure three, we can already see some of that happening, right? So the confidence I score, as you can see right here, it, it fluctuates a lot between different features. So the plotted out the confidence score for each of the 16 features of the graph. Uh, and some of them are highly correlated, while some of them are like zero correlation at all. So yeah, okay. Let's see. Okay, so let's go through this quickly. All right. As introduced in the previous section, okay, the neural architecture search bench graph contains 9 benchmark graphs and 26,000 unique graph architectures. Okay, I see. So that didn't create the graph on their own. Okay. Okay. So they compute the correlation I between the graph topology and the accuracy of the GNNs. Then for each anchor graph, they compare it with other 8 graphs and calculate the correlation, right? Okay, as shown in figure 3, which I did, right, there's a lot of fluctuation, right? So the anchor graph fluctuates a lot. For example, for physics and label homophily, it is positive, but others are negative. That is, some features can be used to judge whether two datasets are strongly correlated on one graph, but the feature might not be, may be unreliable on other graphs. I mean, that's true, right? One feature doesn't work for all different tasks, right? But it may be useful only for some tasks, but not all of them. So, okay, in summary, not only are some semantic descriptions difficult to describe graph similarities, but even statistical empirical indicators cannot be directly used as invariant indicators to characterize the correlation between graphs and the impact of these correlations on model performance. Makes sense? Okay, next. And talking about this adaptive filtering mechanism, right? So, man, this is a lot here. Okay, right. I'm not so sure whether you want me to go through this, but honestly though, let's see, how many more do we have here? So there's a talk about knowledge retrieval module and the GNN suggestion and refinement. You know what? I want to take a look at the results and see whether or not their approach still works at all. Let's see. Okay, for okay, table 1, initial performance comparison of GNN designed by different works, and note that n is equals to 3 for their framework. Right. So using their framework, it's all better. Okay. Right. So for all the graph neural network data sets that perform the best. Okay, that's yeah, that's I can't argue with that. And there's obviously some correlation matrix here, I think. Yeah, and it shows that well, it is obviously the task that's itself will have the strongest correlation. Well, it is certainly interesting to see that around this area, in this area, it's kind of high up in terms of correlation between different data sets, such as Cora with CiteSeer and with PubMed, right? But for others, it's not that correlated. And if we take a look at these things in here, right? So let's see, what do we have here? The best benchmark hit rate across unseen data sets. What they found is that if you give it only like the features to the LLMs, it managed to get the highest benchmark hit rate. Not so sure what that metric means in this case, but because we're kind of skipping over. Right. Let's see. Oh yeah, I missed it. This one, computational resource. Computational resource. Where is the approach here? Okay, I don't really understand this one. But it's probably not that important yet. So how about if I just get to go back to the methods here? All right. Adaptive filtering mechanism. Okay. So, okay, the proposed adaptive filtering mechanism to identify the most influential set of graph topology features, right? So they treat each benchmark graph as an anchor graph and compute the correlation between the graph and the features for each of the 16 features and average them to get the average correlation, right? And then they have a filter function, which is done by using the benchmark data within seconds and selects the top n average correlation as the most influential sets of the topological features. And then and it says that it circumvents artificial hallucination, often by unprofessional or misleading user input. Right, talking about human hallucination here. Okay. Additionally, the design self-evaluation bank, right? So there is a self-evaluation bank (BE) that stores the measure graph topology features and empirical similarities of new datasets throughout the life cycle, ensuring that the filter is always updated. By grounding feature selection on empirical performances on initial model proposals, this mechanism sets the stage for capturing graph-to-graph relationships that can lead to correlations from graph to top performing models. Right, and that's that. It's a bit it's a bit it can be hard to understand that, but I kind of get the gist of that from reading that. Okay, but now let's go through section 3.2 here. Okay, knowledge retrieval, right? Okay, and it talk about auto GNNs often lack this. Okay, proficiency of GNN architecture depends on the ability to accumulate and discern effectively apply knowledge about interrelationships between graphs. Right, shown as this equation here. how, sorry, what is it? Sorry. Okay, oh shit, I think I'm running out of time here. Let me go through this quickly. Okay, to bridge this gap, they use detailed records of model to performance relationships in the NAS bench graph. And then what it did next is try to capture this correlation graph GNN performance. Okay, so they use the top-end model designs from the dataset, right, as summaries of the model preferences for different benchmark graphs. So they associate these models with their future features, um, right, and then they use the LLMs to analyze it, like we show on Figure 1, right, earlier in this video. And compare the unseen similarities between unseen dataset and benchmark graphs. So, so, so this is the holy grail equation here that talks about GPT-4, right? So essentially, you are feeding in the features into the LLM, right? And the task is to generate task similarities that correlate with top performing model patterns. So that's the job of the LLM, right? Then, to retrieve the most relevant knowledge to the unseen graph, we rank benchmark graphs based on their similarities, right? And select top and most similar graphs, right? And that's essentially what this thing does, right? So essentially creating a set of these graphs and the models, right? So this helps to collect top-end model designs from each similar benchmark graph for in-context learning, so that we can give it back to the LMs and then reiterate its proposed designs. So, okay, and last but not least, GNN model suggestion and refinement. So as we already talked about, the LLM is an agent that generates the initial suggestion, but obviously we can do more. We can try to refine it by using a re-rank mechanism, control exploration, model promotion mechanism, and some kind of a directional exploitation and optimization approach. Yeah. So overall, I think this entire approach is quite intuitive, right? Right. So this is a neural architecture research paper, and I think that this approach is right. I wouldn't say it's that yeah, I wouldn't say it's that out of the box, right? Because like I'm pretty sure there's a lot of papers that already done this approach, but just not on graph neural networks. I mean, we could possibly make like improved designs for vision transformers, but using large language models to replace the human part. Yeah. So that's it from my side. Yeah, so go check out the paper if you want to. But that's it from me. Make sure to like and subscribe, and yeah, I will catch you all in the next one. Bye.